equation, a problem.
My name is Mariana Vega.
My name is Paulina Mirandillo.
My name is Samantha Contreras.
My name is Johan Peña.
And we are
Team number 5.
Tres.
In this project, we investigated about rational functions and its applications, slanted asymptotes, piecewise functions, and absolute value functions. So, what is a rational function? In mathematics, a rational function is any function which can be defined by a rational fraction. An algebraic fraction, such as both the numerator and the denominator, are polynomials. So, how you obtain a slanted and an oblique asymptote? A slanted asymptote occurs when the polynomial in the numerator is in a higher degree than the polynomial in the denominator. To find the slant asymptote, you must divide the numerator by the denominator using either long division or synthetic division. The applications for rational functions is that they can be useful tools for representing real-life situations and for finding answers to real problems. In particular, they are quite good for describing distance, speed, time questions, and modeling multi-person work problems.
Right. So, for the people who doesn't know what a piecewise function is, it is a function in which there is another functions like a piece. That's why it's called piecewise function, in which it like grabs like different parts of the same function, just so you can record better the information. Okay, so the definition of an absolute value function is like an algebraic expression in which its symbols have an absolute value. To graph an absolute value function, you have to choose several values of x and find some ordered pace, that is y is more or equals to 0. Okay, so an example of a piecewise function will be like in a graph you have like a car which accelerates in 0 to 2 seconds. It will be like the first part of the function. Then it getting from 0 after acceleration to 100 kilometers per hour. It takes like from 2 seconds to 12 seconds. And from the deceleration from 100 kilometers to 0 kilometers will be like 12 seconds to 25. So it will be like the first piece of the function, then the second, which will be from 0 to 100, and then the deceleration. Right, so another example for the piecewise function will be like if you have a meeting at 9, so you are at the place 8:30. So you will be waiting for from 8:30 to 9. The meeting will be from 9 to 10, and then you're going to your house from 10 to 10:30. So the first piece will be from 8:30 to 9, then 9 to 10, and then 10 to 10:30.
The main difference between these two graphs is that this one is more exact. The key points of the graphs are the intersections. In the x intersection is in -2, 0, and in the y intersection is 0, -4.
Now that we have this original equation, we factorize it into this one. But since we cannot factorize any more at this point, we know we don't have a gap. But now vertical asymptotes, we have 2. That would be -1 and 2. Okay, and for the horizontal asymptote, we can see that the x of the numerator has a power bigger than the x from the denominator. So therefore, we don't have a horizontal asymptote. Now for the intersections of x, y equals 0. So we put the original equation, and this we multiply it by 0. Now we have x to the power of 3 plus 8. We take 8 to the other side, and now it's minus 8 equals x to the power of 3. And now we have minus 2 equal x. That leaves us with the intersection being minus 2, comma 0. And for the intersection of y, we equal x to 0. And we have now 8 divided by minus 2, and that leaves us with minus 4. That being the intersection 0, comma minus 4. For the domain, we know x belongs to minus infinity, comma minus 1, not included, union with minus 1, comma 2, not included, union of 2, comma infinity, not included, and the range is y belongs to all the real numbers. Now in the graph, we can see first the intersections with x is minus 2, comma 0, and with j is 0, comma minus 4. We also have the two vertical asymptotes, one in minus 2 and the other one in 2, comma 0. And then we have to do the long division since we need to calculate the oblique.
So to obtain the oblique asymptote, we need to do the long division. So this is our original equation, and we're going to put the part of the numerator inside the box and the part of the denominator outside the box. But we need to fill in the spaces. So we are adding 0x to the second power and x to the first power, so it's going to be 3, 2, 1 and without the x. And outside is the exact same thing. So if we have 3 elements here, we're going to start putting the letter or number in the third element. So this long division stuff, like how much do you need this element to be exact, like this one. So you have an x. So it's x per x to the second power is x to the third power, but you're going to change the sign every time. So it's plus per plus, you change to minus, so it's going to be 0, and then you x per x, plus per minus, so it's plus, and it's x to the second power, then it's x multiplied by minus 2, but you change the sign to plus, so it's 2x, and then you solve like a normal operation. X to the third power minus x to the third power is 0. 0 plus 1 is 1, and 0 plus 2 is 2. And then you add the 8, so you have 3 elements now, as in the beginning. So how much do this element need to be the exact same as this one? Multiplied by 1. So you use 1 multiplied by x to the second power, and you change the sign, so it's minus x to the second power. 1 multiplied by minus x is plus x. 1 multiplied by minus 2 is minus 2, but change the sign to plus 2 plus 2. So you again solve this as a normal operation, so it's x to the second power minus x to the second power 0, 2 plus 1, 3, 8 plus 2, 10. So this is the oblique asymptote, that is this one.